Today we are going to continue our discussion on the lecture 5. This is again the physics of semiconductor, but here we are looking at the carrier statistics. That means how we calculate the electron or hole density in the semiconductors. I would say this lecture is one of the most difficult lectures among the semester because there are some physics, some equations. But I will go through it slowly, and after today's lecture, you should be able to work on your last few questions in the homework 1. All right, so this is the reference chapter in the textbook, and Professor Asif Khan's lecture, recorded lecture. Okay, so let's look at this band diagram. So from now on, we are going to use this band diagram to discuss the silicon, and later we are going to use this band diagram to look at the transistors as well. So this is very important diagram. So this diagram is respect to the energy. It's about the energy of electron. So here what we draw along this axis is the energy of electron. And we have seen this filled states and empty states, those two bands, and the band gap in between. So here we are going to give a name to the empty states, and we call it conduction band. And then for the filled states, we call it valence band. And in the energy level, we are going to use the EC to represent the edge of the empty states or the conduction band, the bottom edge. And similarly, EV, the top edge of the valence band. So this is totally by definition. And then we are going to introduce a conceptual level, energy level, called Fermi level, EF. And we'll spend the next few slides on this Fermi level. But first of all, I would say the Fermi level is normally in the middle of is inside the band gap. It's somewhere in the middle. And the Fermi level is not a real level, it's a conceptual level. Because as we just mentioned that in the band gap, the electrons are not allowed. So that means the electrons will not really stay on that Fermi level. So it's just a conceptual level, which will help us for the analysis in the following. Okay, so why are we interested in this Fermi level? Because it will help you to answer this question. What is the probability of finding an electron at a particular energy level? So this is given by this so-called Fermi-Dirac statistics. So here let's read this statement. The probability of finding an electron at a particular energy level E, if your electron has energy level E, provided there is an available state at E, is given by this Fermi-Dirac statistics, most often called the Fermi function. So this is the Fermi function. It's a probability F as a function of energy level E, and is given by this 1 over 1 plus exponential E minus EF over kT. kT is the thermal energy. T is the temperature in the unit of Kelvin. K, this small k, is the Boltzmann constant. It's a physical constant parameter. So how do we interpret this Fermi function? First of all, we can look at what if your electron energy E equals to EF. So what does this mean? If E equals to EF, you can plug into this equation, right? So it's 1 over 1 plus E. E minus EF will be 0. So E exponential function, if you have 0, then what do you have? 1. So it's half. Right. Question?
So you said that provided there's an energy level at E, then I can get them probability. But I can plug any value of E in here.
Yeah, you can plug in, yes. Yes.
So this provided thing is...
Provided, we will see that in a minute. Yeah. Because in the band gap, you don't have less this available.
And then we compute it from
That means in the band gap, you cannot have electrons there. Yeah. We'll go to that point later. Nice. So here if E equals to EF, it will be half. Okay. But of course, this is a probability, right? It doesn't mean anything real. So that's why I said in the previous slide we cannot read. This is just this Fermi level is just a conceptual level. Okay. But what is more important is we look at this. If we plot this function into this kind of figure. So let's do this. This will help you to visualize this function better. So here we draw this function this way. So here the y-axis is E, and the x-axis is Fe. So this is a little different than the conventional way of drawing a function, right? So you know the variable, the E, normally we are going to rotate this by 90 degrees. So you get Fe as the y-axis and E as the x-axis. But here we want to make the E as the y-axis because we always want to use this, let's say, the vertical direction as the energy level. So let's say if at T equals to 0, if T equals to 0, okay, this is at absolute 0 temperature. This function becomes 1 plus if your energy E is not higher than EF, then you will get some positive number, right, divided by some positive number divided by KT. And T is 0, so it is divided by 0. Some positive number divided by 0, you will get what? You will get positive infinity. So basically you get positive infinity here. And you know positive infinity, of course, is a very large number. Then essentially it tells you this is 0. This is when E is larger than EF, when T equals to 0. So that means here is 0, this E is 0, this Fe is 0. Remember, the Fe is a probability. So probability 0 means the electrons will not be there. You will not find the electrons there. Electrons cannot be above the EF. Similarly, you can do the E smaller than EF, then the Fe will have 1 over 1 plus E. In this case, you will get some negative infinity number. So negative infinity, you have that in the exponential function. So you get what?
1.
0. I mean, this term will become 0. Recall the exponential function. So the tail, it will approach 0 when you go to the negative infinity. So then this will become 1. So essentially that means if E is smaller than EF at T equals to 0, then the probability becomes 1. That means you will always find the electrons below the EF. Or in other words, this function becomes a step function, very sharp transition here. Of course, in reality, we will have temperature larger than 0. Then if you draw the function with temperature larger than 0, it will become something like this. You will have a gradual transition of the probability from 0 to 1 with this transition. But at Fermi level, here, you will get half of the probability. And as you can imagine, if we further increase the temperature, so this transition region will become wider or narrower. Any idea? If the temperature goes higher?
Temperature goes higher, you get to 1.
So temperature goes higher, then this transition will become wider. Because at temperature equals to 0, this is really sharp, right? And then as you increase temperature, then this will spread out. This will become broadened. So this is how you visualize the Fermi function. Or you can think in this way. So this Fermi function essentially comes from the thermodynamics. And we talk about the electrons. The reason we can find the electron at different energy level is because of the thermal statistics. We talk about that when you have thermal energy, then electrons will vibrate, jump, right? So how high it can jump is a probability. So sometimes it can jump higher, sometimes jump lower. So this Fermi function tells you about this probability. Of course, higher temperature, then more chances then this electron will jump to higher energy. So that's why you see in the Fermi function when you have much higher temperature, for example, the green one, you have this broadened distribution. You have more of the probability to find electrons with higher energy. This is due to the thermodynamics. The electrons are vibrating. So then the probability to find the electron at certain energy level is given by this statistics. Any questions? Okay, so let's look at the approximation of this Fermi function. And here this is a Boltzmann approximation. We are interested in the condition when the energy level is much higher than the EF. For example, if the EF, the E minus EF is much larger than KT, that means your energy level is much higher than the EF. Then we can simplify the Fermi function to this Boltzmann function. So let's do this. So this is your original Fermi function. So this is the original function from the previous slide. And if E minus EF much larger than KT, that means E minus EF over KT much larger than 1. So that means this term much larger than 1. So it's exponential function. You know, if it's exponential function much larger than 1, it's a very large number. If it's a very large number, you can basically ignore this 1. Right? So it becomes 1 over E minus EF over KT. And then this is the same as this one. because 1 over some exponential function, you can move the negative sign here. All right. And here then we are essentially looking at the tail of the Fermi function. Because here, this is already, let's say E minus EF is already 3 kT. So this energy level is above the EF by 3 kT. And then we can apply the Boltzmann approximation to the tail. Essentially, you are going to have an exponential tail here. And then we can also look at other conditions, which is here. This is the energy level much lower than EF, or this E minus EF, much lower than this. So we can also do the approximation. But you have to use this kind of ternary expansion. If x is a very small number, then you can get this kind of ternary expansion. If x is very small. Then if you use this ternary expansion, then you will get this kind of approximation. To describe here. Or we can think this way, if we want to look at this tail. If you want to compare the Fermi function versus the Boltzmann function, so what's the key difference? So let's draw the exponential function in the, let's see, let's rotate this by 90 degrees, because this is F, E, and this is E. So if we rotate 90 degrees, so we have this. And then the Boltzmann function is an exponential function here. Basically, will tell you the distribution will be something like it's an exponential function like this. So this is the Boltzmann distribution. But the Fermi function will give you actually something like, it will be capped at 1, the probability. This is 1. And this is half. This is a Fermi. This is Boltzmann. This is Fermi. You see those two functions, if you plot it out, it will be something like that. So those two will approach each other when at that tail, which is this tail. But the Fermi function will not explode like the exponential. It will be capped or saturated at 1. It's like here or here. So any questions? So this is how you visualize the function. All right.